Welcome to the lesson on continuity and the intermediate value theorem. This is section 2.4 in your text. So a definition here, a function is considered to be continuous if it has no holes, jumps, or asymptotes. Another way to say this is you can draw the function without picking up your pencil. Okay. So here's three examples of graphs that are not continuous. So the first one shows the hole. So we have just a hole here at x equals a, and you could think that the reason we call it removable is you could plug that hole pretty easily with just putting a point in. The second type of discontinuity, again, these are all not continuous or discontinuities. Spell check on that one. All right, is a jump, and that's where you have from the left and the right at a, there's basically a gap here. Okay, so that's not considered to be removable. The last one is an infinite discontinuity, and that's where you have the asymptote. Here the asymptote is at x equals a, where from the left we're going infinitely high, from the right infinitely large in a negative direction. So let's take a look at a continuity at a point. Here is a definition for a function f to be continuous at a point x is a. We need three conditions to be met. One, the function has to be defined. Two, it has to have a limit that exists at the value where x is a, or as x approaches a. And the last thing is that the limit needs to be equal to the value of the function at a. So those have to be the same. So if you want to check and see if something's continuous at a point, you can just kind of go through this list in that order. If it breaks any of the three, then it's over. All right, let's take a look at an example. Determine whether the function f of x is x squared minus 4 over x minus 2 is continuous at x equals 2. Justify. So we can just consider number one, which is just checking f of 2. We'll just plug 2 into the function. 2 squared minus 4 over 2 minus 2. We get 0 over 0. You can see that's undefined. So our conclusion is not continuous at x equals 2 because f of 2 is undefined. In that case, we did not even get past number 1. Let's take a look at the one on the right. So this is a piecewise function. It says given f of x is sine x over x when x is not 0 and 1 when x is 0, determine if it's continuous at x equals 0, justify. So we want to go through them piece by piece. So the first one is we're looking at x is 0, so we want to think about f of 0. That would mean we're going to look at the bottom function. So when x is 0, the function is just a value of 1. There's really nothing to evaluate. 2. The second part is what is the limit as x goes to 1? And so, well, we don't have a picture here, but we can draw upon our knowledge from the previous lesson. We know that at 0 it is 1, but what's it doing with the top part when x is not 0? That would be the limit as sine x over x goes to, I put 1, but it goes to 0. All right, let me fix that. Okay, well, this is from section 2.3. The definition of this, and we went through the squeeze theorem to prove this, the limit is 1. And so in number 3, we want to make sure that these two match. We can see, yes, they in fact are both 1. F of 0 is equal to the limit as x goes to 0 of f of x. So it's all three are satisfied. So we say is continuous at x equals 0. That's the proof as long as you have all three. Okay, let's take a look at these two. If you want to pause the video and try them yourself, you can. Notice they're both piecewise functions. Okay, if you tried those, let's kind of go through these three. So the first one on the left, let's go for the first part is we want to see if it's continuous at x equals 3. We'll think of f of 3. Notice the top part is the part that contains where it's equal to 3, so we'll plug into that function. So we have negative, notice there's no parentheses, so the 3 is going to be squared, but not the negative. All right, we'll get negative 9 plus 4 or negative 5. That's fine. If we look at the, if we think about this as possibly being a jump or a break, it's definitely not an asymptote. Nothing's going to infinity here. We're for part 2, we're going to consider what is the limit as x goes to 3. Now we already looked from the left. From the left, that's that top function. That's the negative 5. We need to consider the limit from the right, when we consider this function. So we're going to take a look at that other piece of the continuous function. We're going to consider plugging in our value of 3 into that to see what we get. We get 12 minus 8, and we get 4. Something's going on, right? So limit does not exist, and that's because from the left we get a value of -5. That is when we plug into the top function. But on the right, when we plug in 3, we get a value of 4. So not continuous. And that's because although this passed, this failed. Not continuous at x equals 3, since the limit does not exist. All right, so last one. This one is a piecewise function that's in 3 parts. It's when x is less than 1, 1, or greater than 1. And so we're really trying to see is, do these three parts kind of come together in one thing that you can draw without picking up your pencil? Well, what are the 3 parts? One is, what is f of, in this case, we're looking at x is 1. What is f of 1? That's just this middle piece here. All right. When x is 1, the value of the function is just 2. If we want to consider the limit, we might consider the left-handed limit and the right-handed limit to see if they match. So let's take a look first at the left-handed limit. When f of x goes to 1 from the left, we're going to be using this top piece, right? That's when x is less than 1. So we're going to plug in 1 into 2x plus 1, and we get 3. Now let's take a look at the limit as x goes to 1 from the right. And that will be this bottom function when x is greater than 1. So we'll plug in our 1 there. We'll get -1 plus 4. That is also 3. Okay, cool. So that means since the left and the right are the same, the limit does exist at 1, and it actually is the value of 3. Unfortunately, part 3, right? Notice our value here and our value here did not match, right? So f of 1 is not equal to the limit as x goes to 1 of f of x. So we conclude not continuous at x equals 1. All right, so we have cases of continuity and discontinuity for different reasons. Okay. Next page. Although a function may be continuous at 1 or more points, it may be continuous over a given interval. And I think I said that wrong, but discontinuous, it might have a place of discontinuity. There might be a place where you have a jump or a hole, but it doesn't mean that it's not continuous over a specific interval. So let's take a look at what we mean with these examples in just a second. But let me show you with a picture kind of what I'm getting at. Is you might have a function, let's say a function that goes up, okay, kind of terminates here and then jumps up here and then maybe does something else over there. You definitely have a discontinuity. I had to pick up my pencil, but if you limit the domain in a specific interval, like if I look from here to here, I can draw that portion of the graph without picking up my pen. So I would say that it's continuous over that specific interval, even though it's not continuous over the entire domain of the function. All right, example 1. For what values of x is the function continuous? Okay, so we have this rational function, x plus 1 over x minus 5. I want to think about what could make this discontinuous. And the only issue I see is I could have a divide by 0 error, right? Divide by 0 error. And that's when the denominator, this piece, would be 0. And that's pretty easy to do in our head, but I'll write it down. When is x minus 5 equal to 0? Well, that's when x is 5. So that means that this graph has a point of discontinuity. I'm just going to write that in. It's discontinuous at this value, and that's because it's just not defined. But before 5 or after 5, we have no problem. So I'm going to state my solution as continuous on interval from -infinity up to 5, not including 5, and then from 5 onwards to infinity. In other words, that's kind of a way of saying everything except 5 itself. All right, number 2. For what values of x is this function continuous? I can see that I've kind of drawn a little bit of a mark over the top of that. There we go. So it's 2x minus 5 over x squared minus 5x minus 14. Sometimes if you will graph, you get a better idea, but to stay away from that, let's just take a look at another way to consider it is to factor. So I'm going to factor that denominator. I see a trinomial. Let's see, we have x times x gives us x squared. We have 14, so I have 7 and 2 minus and plus. All right. What this does for us is it lets us see pretty clearly what values of x will cause a discontinuity. Notice if I have a value of 7, that will cause the first factor to be 0 because 7 minus 7 is 0. So x to 7 is an issue. And then here, for this second factor, if I have negative 2 plus 2, I get a 0. And so that means I have a discontinuous position at x is negative 2. And so let me say this in two ways. It's discontinuous at x equals 7 and x equals negative 2. So this one says, for what value is it continuous? So I'd say continuous everywhere else. And everywhere else would be from negative infinity up to negative 2, and then from 2 to 7, and then from 7 onwards to infinity. In other words, everywhere except negative 2 and 7. All right. Next part. Let's take a look at how we might classify those. Now, classify is kind of what I started off with this lecture talking about. Does it have just a hole, a removable discontinuity? Does it have a jump? Or does it have this infinite discontinuity, kind of a vertical asymptote? So on page 1 of the notes, we found that this function right here is discontinuous. But what kind was it? What exactly was going on there? So, well, if we factor this function, it gives us a little more information. The top happens to be a difference of two squares. It'll factor to x plus 2 over x minus 2. And then notice that if we were to simplify this function, we can think about it that it's going to behave a lot like x plus 2. Now, I'll give you a visual, and it'll help you think more about this, I believe. Since this function simplifies to x plus 2, it's going to graph or behave just like the line x plus 2. Oh, well, we know something about that. That's a line with y-intercept 2, and the slope is just 1x. So it's going to be something like up 1 over 1. Now, that's a graph of x plus 2. But our question was really about this original function. Although it behaves like x plus 2, it has a point of discontinuity at x equals 2. Remember, that was the problem. So that means that my graph here is not completely accurate, because over at 2, there is an issue. There is going to be a hole up here on the graph. And maybe I need to delete that or just redraw that. So let's see, here at 2, we're going to have a little open spot, and it's going to, let's see if I can draw that a little bit better. It's going to go on. So in other words, it's the whole entire function will look like a line, although mine doesn't look very straight, but it will have a removable discontinuity. That is our classification, removable. Another way to say it is it has a hole. All right, and the way we recognize that is sort of this simplification of the factoring. Example 2, we also had this piecewise function from page 1 that was discontinuous at x equals 3, classify the discontinuity. Now you might recall me kind of doing this, but when we plugged in the value of 3 on the left port, we got negative 3 squared plus 4. To do that one more time, negative 5. Whereas we plugged in 3 for the right-hand portion, 4 times 3 minus 8 is 4. So these values don't match. So we seem to have a jump there from one to the other. And I believe I already graphed this on the first page, that I already give you a sense of what that would look like. But it's really just considering the limit, if you want to write it in, of x that goes to 3 from the left of the function versus the limit as x goes to 3 from the right of the function. All right? So let's take a look at example 3. Okay, notice on this example that the numerator and denominator don't factor anymore, and they have no factors in common. So there's no way to think about that as a removable discontinuity, in the sense that we can't simplify this so that it behaves like a different function. So we would probably just want to think about, in this denominator, what would cause this to have a discontinuity? That would be at x is negative 1. So I'm going to consider that to be a discontinuity. So what that could mean for us is that if we had a graph of this, at negative 1, we're going to have some kind of asymptote. And if you have more experience with rational functions, you might have a good sense of this. But in essence, what's going to happen is, if we look at the limit of the function as x goes to this discontinuity point, which is negative 1 from the left, we're going to get something, well, let's just think about the numbers. In the numerator, we're going to have, well, first of all, what do we mean by negative 1 from the left? That would be slightly smaller than negative 1, like negative 1.0001, something like that. So we're going to have something positive on the top, a number close to 1. And then on the bottom, we're going to have something that's negative 1.0001 plus 1. It's going to be just a very small negative number. So as this gets close to negative 1 from the left, it's going to just get infinitely small. Now, as it goes out, it actually is going to have a horizontal asymptote there. We'll talk about that more later in the course. It would be at a value of x is 1, but don't worry about that so much right now. What really is important is that this goes to negative infinity. Then if we look at the limit as x goes to negative 1 from the right for this function, we're going to think about a number that's slightly larger than negative 1, like negative 0.9999. Again, we're going to have something close to 1 on the top, and on the bottom, we're going to have something very, very small but positive. So it's going to get infinitely large from the right, and then it'll go out that way. That's not a perfect graph, but you get the idea. So this would be not jump, don't write that. It's going to be an infinite discontinuity because it has that infinity value from left and right. It doesn't have to be going to a different direction. In this case, it does go negative and positive. They can either go both positive or both negative. It'd still be considered an infinite discontinuity. All right. Number 4, we have a piecewise function given h of x is x squared when x is not 1 and 3 when x is 1. Find and classify any discontinuities. So we know at x is 1, the value is 3. Let's consider, though, so let me write that down. H of 1 is 3, but when it's not 1, it's going to behave like what is the x squared. So let's take a look at the limit of the function as x gets close to 1. We don't have to do a left and a right here, probably so much, but let's go ahead and write it anyway. What is 1 from the right? Well, from the right, it's going to be this top function. So we're just going to think about it. Oh, it's 1 squared. 1. What about the limit as x goes to 1 from the left? Well, since this is the only other function, that's exactly going to behave the same way, is that the function from the left and the right is still going to be on the x squared. It's just going to be 1 squared again, or 1. Oh, okay, so that must mean our limit then as x goes to 1 of h of x is 1. So we know we have a discontinuity because it's 3 at the function, but then the limit is 1. So what we have graphically is we have this function x squared. It's just that regular old parabola, except somewhere along maybe around here, when x is 3, we have a place where there's a hole. And instead of that hole being plugged, because this value is 1, right? 1 squared is 1. The value of the function at x is 1 is actually 3. So there's a hole there, but then the point is up here. Okay, so this is what we call a removable discontinuity, because you can just plug that hole. And so it takes a little bit of analysis to get some of this, but that's the basic idea of how you can classify between the different types of discontinuities. All right, so this last one, find k such that the function below is continuous everywhere. So again, what we're wanting to be able to draw this without picking up our pen. So notice the top part of this, the first part, when x is less than or equal to 1, is a linear, 7x minus 2. So maybe we have, some function, 7x minus 2. It's coming along. At some point it stops at x is 1, right? So it's some kind of linear function. That's not a perfect graph, but go with it. And then after x is greater than 1, it behaves as a quadratic. Now the problem is we don't know what the quadratic looks like. Maybe the quadratic will in fact go through this point, like maybe it's something like that, and then that would be something I could draw without picking up my pen. But what if it jumped down here and it was something like that? That would be discontinuous. So we want the left and the right spot, we want them to match at x equals 1, because we don't want to jump from one to the other. So we're just going to set the top equation, 7x minus 2, equal to the bottom equation or formula, kx squared plus 2, when x is 1. We want the left and the right to match. That means we can just plug in 1 for x. So plugging in 1 for x here, we get the left-hand side to be 5. And then plugging in 1 here for x squared, let's just do that in our head. 1 squared is 1 times k. And so solving for k would be 3. That would make that happen. All right, that's our value of k that makes it continuous everywhere. So the left and right match. Okay, next part is the intermediate value theorem. The intermediate value theorem, let me see if I can just scroll over just a little bit so you can see this a little bit better. All right, let f be continuous over a closed bounded interval from a to b. If z is a real number between f of a and f of b, then there is a number c in that same interval, a to b, such that f of c is z. Now, I can tell you right now that's a mouthful, and you might need to read that 3 or 4 times, 5 times. But maybe a picture can really, really help you. Okay, so you can see here I have a graph here, and I want to draw something continuously from a to b. Now, notice here on the bottom left, right here, I have a point at a comma f of a, and I have a point up here on the right at b comma f of b. All right, those are the. So I want to draw something basically without picking up my pen. And it could be many things. It could be a straight line from there to there. It could be curved. It could be, that's one way to do it without picking up my pen. And so let's go back and see what this theorem is saying. If it's continuous, as I did there, right, over this closed bounded interval, I didn't pick up my pen, and z is a real number between f of a and f of b. So let's take a look at what that means here on the graph. Between here, that's kind of messy. Between here and here, right? That's between f of a and f of b. Somewhere on that line, I'm going to write it down like this. Z is any number between f of a and f of b. And it doesn't have to necessarily be less than a or less than b. Just in this case, the way that I've drawn it, z would be like that. We want it to be any number in there. There's a number on the interval a to b that makes that true. So for example, if I pick some random spot between f of a and f of b, let's just say right here, that's my z, then we should be able to map that over to the function and find a point on the graph that maps down to here, c, such that f of c equals z. In other words, this point right here will be the point c comma f of c, which is the same as c comma z. In other words, if you started here and you went all the way up to here, you had to catch all the points from there to there. It's not possible to miss a point. Maybe I'll just try to do that by looking at it. Let me try to not do it. I'll show you what I mean. So let's say on this graph on the right, let's say I want to think about this value of z. And so if I drew a horizontal line there at z, how can I draw from the point on the left to the point on the right without crossing the dashed line? You might think, well, I just go around. That's still across the dashed lines. That doesn't count. All right. Well, the only way to get it done would be to kind of draw up here somewhere and then hop over the top and then keep drawing. Well, when you do that, you left a hole there, meaning it's not continuous. So this theorem is basically saying if you have a continuous function, then you must necessarily cross every point, every z between f of a and f of b. All right, so let's take a look at some examples. Show that f of x is x cubed minus x squared minus 3x plus 1 has at least one zero over the interval from 0 to 1. Now you might remember a zero of a function is where it crosses the x-axis. There's the 0 right there. And so you may not remember how to graph this polynomial function exactly, but we can prove this as follows. Let's take a look at the left-hand side, 0. What is f of 0? Well, that's 0 cubed minus 0 squared minus 3 times 0 plus 1. That's my kind of evaluation, 1. What is the right-hand side? What is f of 1? 1 cubed minus 1 squared minus 3 times 1 plus 1. This will take a little bit more thought. We got 1, take away 1. That's back to 0. Minus 3 plus 1 should be negative 2. Well, notice on our graph, f of 0 is 1. Let's think about this graphically. F of 0 is 1. So that's here when x is 0. And f of 1 is negative 2. So we have a point right here. So those are our 2 points. Well, if you draw from the one on the left to on the right, the only way to do that is to necessarily cross the x-axis somewhere. You have 0. Okay, so you can see that with the intermediate value theorem, since f of 0 is 1 and f of 1 is negative 2, then we have to have all of the values between negative 2 and 2. There must be a spot, and 0 is certainly between negative 2 and 1. And so there does exist that point. All right, let's take a look at this next one. Show that f of x equals x minus cosine x has at least one 0. Okay, so Notice that I did not give you an interval on this, so you have to just kind of play with it a little bit. The easiest number to work with is usually 0, so I'll try f of 0. In this case, we'd get 0 minus cosine of 0, which would equal 0 minus 1, or negative 1. So then I'm thinking, okay, if I wanted to have a 0, I have something negative. Now I should have something positive. In other words, I'm thinking in my head, f of 0 is negative 1, or down there. I want something that's going to be above the x-axis up there. What value might give me that? I'm also thinking, well, I have a cosine function. I better pick a value of x where I know, how to evaluate that pretty easily in my head. So I'm thinking, well, pi over 2, pi over 4, pi, maybe something that's good